The taller a building gets, the harder it has to fight wind. Gravity just pushes down, wind pushes sideways, constantly. So how do engineers stop a 500-meter tower from swaying like a tree in a storm? Here's every major structural system that keeps skyscrapers standing. Rigid frame structures. The earliest skyscrapers, like the Empire State Building, used a rigid frame, a grid of vertical columns and horizontal beams, rigidly connected at every joint. When wind pushes on the building, the frame resists by bending slightly at these joints instead of collapsing. It works well for buildings up to around 30 stories, but past that, the frame alone gets too flexible and uses too much steel to stay economical. Tube system. To go taller, engineers came up with the tube system. Instead of spreading columns evenly through the floor plan, you pack them tightly around the building's perimeter, turning the entire outer wall into one giant hollow tube, resisting wind like a closed cylinder. The Willis Tower in Chicago pushed this further with a bundled tube, 9 individual tubes joined together, each one able to stop at a different height, which is why the building's silhouette steps back as it rises. Diagrid system. The diagrid system ditches vertical columns almost entirely. Instead, a diagonal grid of steel crisscrosses the building's exterior, carrying both gravity and wind loads through triangulated geometry. Triangles don't bend the way rectangles do, so a diagrid needs far less steel for the same strength. Hearst Tower in New York is the clearest example. You can see the diagonal pattern from the outside, and it's not just decoration, it's the entire structural skeleton. Outrigger and belt truss system. Tall buildings have a central core, usually concrete, housing elevators and stairs, but the core alone isn't stiff enough to resist wind by itself at extreme heights. Outriggers are horizontal trusses that connect that central core directly to the perimeter columns at one or more levels up the building. This ties the whole structure together, so when wind pushes the core sideways, the perimeter columns share the load instead of the core taking it alone. A belt truss then wraps around the perimeter at that same level, distributing the force evenly. Buttressed core. The Burj Khalifa needed something new to hit 828 meters. Its buttressed core uses 3 wings extending from a central hexagonal core, each wing buttressing or bracing the others. As the building rises, each wing sets back at a different height, which does 2 things. It reduces the building's mass higher up, and it disrupts the wind vortices that would otherwise build up and cause dangerous swaying. Tuned mass damper. Even with a strong structural system, tall buildings still sway. Just not enough to be dangerous, but enough to make people inside feel uncomfortable. Taipei 101 solves this with a tuned mass damper. A 660-ton steel sphere suspended near the top of the building like a pendulum. When wind or an earthquake makes the building sway one way, the damper's momentum swings the opposite way, canceling out much of the motion. It's less about strength and more about comfort. It's essentially a giant shock absorber for the whole building. So which system gets used depends on height, wind exposure, seismic risk, and budget. Rigid frames for shorter buildings. Tube systems and diagrids when steel efficiency matters. Outriggers when you need extra stiffness without adding tons of material. Buttressed cores for super tall records. And dampers when the structure is strong enough, but people still need to feel steady on the 80th floor. That's every major structural system holding up the world's tallest buildings. If you want more deep dives into the engineering behind the structures around you, subscribe to Structopedia. New videos every week.